Hi students, welcome all. Myself Sajeev Aniyath. I am here to discuss chapter 1 relation function in your class 12th. Okay. Today we are going to discuss relation function. First we start from relations. Before starting relation, we have to know what we have studied in your class 11th. That is, first chapter you have studied sets, and the second lesson is relation. Before starting relation, you have discussed about Cartesian product. What is a Cartesian product? If let A and B are two sets, A and B are two sets, then the Cartesian product of A cross B is denoted by A cross B is equal to set of all ordered pair AB. It is a set of all ordered pair A comma B. A is an element of A and B is an element of B. That is, first component is an element of first set and the second component is the element of second set. Okay, what about relation? Relation is a subset of Cartesian product. If a relation R is defined from a set capital A to set capital B, then R is a subset of A cross B. A cross B is the Cartesian product of A and B. Also, a relation is defined from a set to itself, that is from A to A itself. Then it is a subset of A cross A. This year we are going to study about types of relations. What are the two types of relations? That is trivial relation and there are non-trivial relation. Under the section trivial relation, we study about empty relations and universal relation. And in non-trivial relation, we study reflexive, symmetric, transitive. And if the relation is reflexive, symmetric and transitive, we call it as an equivalence relation. That also we discuss. Okay. The next, first let us start trivial relation. That is empty relation. What is an empty relation? You all know about empty set. Empty set is a set containing no elements. Same as the empty relation is a relation which contains no elements. No elements. That is, let us give an example for that. Let capital A is equal to set of 1, 2, 3, 4. Consider the relation R is equal to set of all ordered pairs such that A minus B is equal to 6. Difference between any two elements in the set 1, 2, 3, 4 cannot be 6. So R contains no element, it is an empty relation. R is equal to, we can represent empty relation by 5. Now let us discuss about universal relation. Universal relation is a relation contains, if a relation is defined from A to A, then the universal relation R is equal to A cross A. That is, R contains each and every element of the Cartesian product A cross A. Let us discuss an example, that is A is equal to 1, 2, 3, 4, R is equal to set of all ordered pair AB such that the modulus of A minus B is greater than or equal to 0. In this relation, we can find that difference between any number can be positive or negative, but if it is if it has modulus, then that is it is always greater than or equal to 0. So R is equal to A cross A, then it is an universal relation. Now let us discuss a problem on empty relation and universal relation. Let us consider a set of all students in a boys' school. Let capital A be the set of all students in a boys' school. And a relation is given as R is equal to set of all ordered pair AB such that A is a sister of B. And another relation is given that R dash that is equal to set of all ordered pair AB such that the difference between any two students, that is A and B are students, we all know, and difference between A and B is always less than 3 meters. We have to show that R is a empty relation and the second relation is let it be R dash. R dash is an universal relation. Okay. First empty relation. Let R is equal to set of all ordered pair AB. A is the sister of B. Since the school is a boys' school, no student can be a sister of any other student of that school. We all know that. Then there will be no such ordered pair exist in the relation R. Then R is a null set. That is, R is equal to 5. Then we call it as an empty relation. Okay. What about universal relation? That is, R is equal to set of all ordered pair AB such that difference between heights of any two students is always less than 3 meters. It is obvious that difference between heights of any two students is always less than 3 meters. Then R contains every element in A cross A, that is R is equal to A cross A. Then it is said to be an universal relation. Now let us discuss about non-trivial relation, that is reflexive, symmetric, transitive and equivalence relation. First one is reflexive relation. What about reflexive relation? That is, if a set relation is defined on a set capital A contains, A is a finite set. If each and every element of A is related to itself, then R is said to be reflexive. Let us discuss with an example. Let capital A is equal to set containing 3 elements 13, 14 and 15. Let R be a relation such that R is set of all ordered pairs such that A is equal to B. We have to take ordered pairs such that A and B are equal. Then 13, 13, 14, 14, 15, 15. All the elements is related to itself. So R is a reflexive relation. What about symmetric relation? If AB is an element of capital R, implies that BA is an element of capital R for all A comma B element of capital A. Now let us discuss the symmetric relation with an example. Let capital A is equal to set 4, 6, 7 and the relation R is defined as set of all ordered pair AB such that A plus B is greater than 10. Then R is equal to, we have to take a relation such that sum of two numbers is greater than 10. Let us take 4, 7. We can't take 4, 6 because 4 plus 6 is equal to 10. 4, 7 and 6, 6, 6, 7, 7, 4, etc. elements. We see that we observe that the relation R contains elements 4, 7, 6, 6, 6, 7, 7, 4, 7, 6 and 7, 7. We observe that if the components of the ordered pair are interchanged, they are also in capital R. Then the relation is said to be a symmetric relation. Next, we discuss about transitive relation. The relation capital R is defined on a set capital A. Let us take three elements from capital A, that is A, B, C. If AB, that is ordered pair AB and ordered pair BC is an element of capital R, implies that ordered pair AC is also an element of capital R. Then we say that R is a transitive relation. Discuss with an example that capital A is equal to set 8, 13 and 15 and R is equal to set of all ordered pairs such that A less than B. We see that 8 is less than 13 and 8 is less than 15. We can write 8, 13, 8, 15 and 13, 15. Then it is a transitive relation since 8, 13 and 13, 15 are element of R. 8, 13 and 13, 15 are in capital R. 8, 15 is also an element of capital R. So it is a transitive relation. Okay. Now let us discuss about equivalence relation. What is an equivalence relation? A relation which is reflexive, symmetric and transitive. Then we call it as an equivalence relation. Here one example is given. You can go through that example. Okay. Now we discuss a problem on equivalence relation. Let us take a set of all triangles in a plane. Let T be the set of all triangles in a plane and we can define a relation capital R is equal to set of all ordered pair T1, T2 such that T1 is congruent to T2. That is T1, T2 are triangles which are elements of the set capital T. Here the relation is T1 is congruent to T2. We have to show that it is an equivalence relation. To show that it is an equivalence relation, we have to show that it is reflexive, symmetric and also transitive. Then only we can say that it is an equivalence relation. We all know that each and every triangle is congruent to itself. Then T1 is congruent to T1 itself. For all T1 element of capital T, if we are taking T1, T2, T3, every triangle, each and every triangle is congruent to itself. So R is an reflexive relation. Now we have to show that R is symmetric. For that, let T1, T2, ordered pair T1, T2 is an element of capital R. That means T1 is congruent to T2. That is T1 is congruent to T2. Then we say that T2 is congruent to T1 also. Then ordered pair T1, T2 belongs to R implies that ordered pair T2, T1 is also element of capital R. Then we can say that R is an symmetric relation. Next one is transitivity. What is transitive relation? Ordered pair T1, T2 and T2, T3, that is two ordered pairs are element of that relation capital R. That means T1 is congruent to T2 and T2 is congruent to T3. Then we say that ordered pair T1, T3 is also an element of capital R. That means T1 is congruent to T3. That is the relation is a transitive relation. Here capital R is a relation which is reflexive, symmetric and transitive. Then we can say that R is an equivalence relation. Now let us discuss one more problem on the equivalence relation. Let us consider a set capital Z, set of all integers and a relation R defined on the set Z as capital R is equal to set of all ordered pair AB such that 2 divides A minus B. That is 2 divides A minus B means A minus B is divisible by 2 or A minus B is a multiple of 2. Okay, for showing that R is an equivalence relation, we have to check reflexive, symmetric and transitive. We start with reflexive. We all know that A minus A is equal to 0 is divisible by any number. Then A minus A is equal to 0, 0 is divisible by 2. That means 2 divides A minus A for all A element of that set Z. Then Ordered pair A belongs to capital R for all A element of Z. For any integer, A minus A is equal to 2 is divisible by 2, 2 divides 0, then R is a reflexive relation. Then what about symmetric? Ordered pair AB belongs to capital R, that implies A minus B is divisible by 2, that is 2 divides A minus B. We can say that A minus B is a multiple of 2 or A minus B is divisible by 2. Okay, if A minus B is divisible by 2, we can say that B minus A is also divisible by 2, then R is a symmetric relation. Now let us consider transitivity. Let ordered pair A be element of R and ordered pair B is also element of R. That means 2 divides A minus B and 2 divides B minus C. That means A minus B is a multiple of 2 and B minus C is also a multiple of 2. That is A minus B is equal to 2m for some integer m. Now B minus C is an element of R. That means 2 divides B minus C. Then B minus C is also a multiple of 2. That is B minus C is equal to 2n for some integer capital N. Just we add A minus C. Now A minus C is equal to A minus B plus B minus C, which is equal to 2m plus 2n. Taking 2 outside, we get 2 times m plus n. It is a multiple of 2. That is A minus C is also a multiple of 2. That implies A minus C is divisible by 2. That means 2 divides A minus C. Then ordered pair A minus C is an element of capital R. Thus we have shown that R is a transitive relation. Here capital R is reflexive, symmetric and transitive. Then we say that it is an equivalence relation. Hope you all have understood the concept of the relations, types of relation, equivalence relation. Thank you all. See you in the next video.